Mm.
So what you would have is like hot plasma. That's the state of the universe. We know exactly that's where things started. But the
Yeah.
question is, how do you get from plasma to us, to galaxies, to stars,
Okay.
to planets? That's a big
Great.
question. Parts of the universe that were left over from the Big Bang are still here. The universe is very old, about 13 billion years
Mm.
old. But its signature, what had happened during the Big Bang, it's still out there. All we need to do is to look out into the night sky. And there's a whole science argument that you can frame how you can do that. And all you need to do is look out in the night sky. And so what we're trying to do is answer this question, nail it down. How does the universe form? How do we get from no galaxies to galaxies? And I am a staff astronomer at the South African Radio Astronomy Observatory. This is based in Cape Town. It's a big facility which manages the world's best sensitive radio telescope. And yeah, and I'm one of the people in the research group there. But in my own field, I am actually what I did in my research field is cosmology. And cosmology in itself is a very nice field. In the simplistic term, it's more of a revision of Genesis chapter one. We uncover, well, we have an alternative way of looking how the universe was formed. So there are different branches in general in science. So cosmology looks at how did we start off? And then there's the local stuff, like the stuff that you see in the night sky, the galaxies and all the stars. And like when you look out in the night sky, you always see these tiny dots of lights in the sky. That's different. So that's astrophysics because you study what the local environment is. The universe turns out is it's a lot bigger than what people think.
Mm.
Of course, of course,
Okay.
we've come to this knowledge because, advances in technology and all that kind of stuff. But then came cosmology eventually. So cosmology is much more of a like a frontier, I would say so. It's
Mm.
where most of the knowledge is still missing. Okay, but we got, it's a pretty much picture that we've painted. Well, I'll try
Okay.
to explain in a moment
Okay.
where I'm getting to that. But whenever we do these things, you study your local environment. And what we do is there's a term that we call extrapolate. In other words, you infer that, well, maybe perhaps what you're observing locally is
Mm.
also true for the distance things. Like, I mean, there's no reason to think that they're different. And that's where cosmology comes in.
Mm.
Because we have a good idea how our universe started. We know it from all the way to up to 1 second from what we call the Big Bang model.
Mm.
And that's basically what we do. We try to, well, how do we get a universe from a simplistic universe where there was only
Mm.
just gas? Uh, the other day I was chatting with another guy who was just telling me that, oh, actually, cosmology is gas all the way to forming human beings.
Mm.
That's that's the entire picture that we're trying to paint. It's not easy because it incorporates a lot of things, like your astrophysics, the stuff that we study locally.
Mm.
And also then there are some things that you can't actually see without telescopes at the moment. So you kind of have to infer, you have computer models and all that kind of stuff. But that's basically what we do. It's never, well, science, in science in general, it's never just good to, how should I put this? You can have an idea
Mm.
about how things work, but if that's not supported by the data, well, it's
I
not,
see. I see what you
it's
mean.
not a good enough like it doesn't,
Yeah.
it's not a good enough theory. There needs to be actual factual evidence backing that up, and
Correct.
that's what we do. Now, the difference between what an undergraduate would do, maybe
Yeah.
like you can, if people were doing experiments back in the days, when you're doing lower grades in high school,
Mm.
you would remember you do experiments, and then you can't you will do the experiments, uh, capture some data, trying to make some
Mm.
scientific conclusions from that. The difference is this one is a huge experiment, a very big one, a very costly one, and a very technical one. So we are also doing the exact same thing, performing an experiment, trying to get the data, see
Mm.
if our models work. And that's what MeerKAT and other what should I say, other radio telescopes that are there. I will
Yeah.
talk about MeerKAT, but
Yep.
the first one that I want to talk to you about is the hydrogen Epoch of Reionization array. That is the one that's besides MeerKAT. Um, if you look geographically, you'll find it, and that's a pristine sort of instrument. It's actually
Yeah.
looking for the very first light. So let me try and explain how the Big Bang model is
Correct.
formulated. Right. So 1 second after the Big Bang, there are various states of matter. Okay. If you remember from your physics classes or anything
Mm.
like that, uh, you have your solids normally. Let's say you take water for an example. Water is
Mm.
icy when it is at a lower temperature.
Right.
Okay. Now you can imagine heating that water up. Eventually, it turns into liquid because the molecules have what we call kinetic energy, so they can move around. So now it's like a
Mm.
liquid. You heat it up more, you get water vapor. So water becomes, it's in a gaseous state. Now, the more you increase the temperature, then the water becomes ionized. Basically, what it means to be ionized is that
Mm.
electrons are stripped off from
Yeah.
um, from their atoms, and then the state of matter is a plasma in that sense. And so we have a pretty good idea. So whenever we look out in the night sky, there's this radiation coming from everywhere uniformly around the sky. And this radiation has a certain temperature that our models predict, and it
Mm.
measured it, and it confirms. What that basically says is that at some point, the universe was incredibly hot, that you couldn't even have your normal neutral elements like your hydrogen or anything like that.
Mm.
So what you would have is like hot plasma. That's the state of the universe. We know exactly that's where things started. But the
Yeah.
question is, how do you get from plasma to us, to galaxies, to
Okay.
stars, to planets? That's a big
Correct.
question.
Which which
Mhm.
which which takes me to, how does this all start for you? Can you just take us back a little bit
Take us
into,
back a little bit. All right.
yes, take us back a little bit and walk us through how this starts to click and things starts to make sense and build
Start to
interest.
make sense.
Yes.
Build interest in astronomy. There's always this sense of we don't know much about our world, okay,
Okay.
how things work.
Yeah.
And so for me, particularly, it basically started from simple concept. How does an engine work? Like
Okay.
how does simple things like optics, how do lenses work? How does the TV work?
Yeah.
For sure, people have already figured that out because they invented the stuff. But what you get to uncover there is the inner workings of nature itself,
Mm.
which kind of brings that inquisitive mind as, oh well, it looks like this is what we're getting.
Mm.
Then when we started building technology, for an example, when we had telescopes, and then for me, when we had telescopes, for an
Yeah.
example, I had this one nice view of the Earth where we had this huge Earth flat plane and then all the tiny stars. I think it's
Yeah.
called the flat Earth model.
Mm.
That's where everybody kind of
There's
starts from
a whole
because
thing
that's
now
how it
about flat
looks.
Earth. There's a whole thing now
Exactly.
about flat
Exactly.
Earth that, all sorts of theories and all sorts of
Theory.
arguments and all sorts of really strong arguments are coming about flat Earth. So maybe you are more in a position to maybe either not support or support that kind of understanding
Yeah.
about how did the flat Earth come about. If the Earth is not flat, then are we not tilting the other side? But are you seeing
What's
something that
happening?
confirms this?
No, the Earth isn't flat.
Okay.
That we know. We definitely know for sure, right?
Okay.
But I can certainly understand someone who would think that the Earth is flat. I
Mm.
can certainly understand because it looks like it is flat from a
Mm.
human perspective.
Yes.
But then that's why you need to develop some technology. You need to develop some clever ways, okay, in order to decipher that, oh, actually, the Earth isn't flat. For an example, if you understand that there's a lunar eclipse, for an example,
Yeah.
in a flat Earth model, you can't kind of explain what a lunar eclipse is. And the lunar
Yes.
eclipse is basically where the Earth is in between the sun and the moon, and the and
Correct.
and the and the and the and the Earth's shadow is cast on the moon.
Mm.
You kind of explain that with the flat Earth model. And so, for instance, why is it day and night? Why do ships dip as they move away from the shore? When you're standing by the beachfront and then you look at ships, they tend to dip away as they move away from you. They tend to dip a little bit, and that's because the curvature of the horizon, basically it's dipping down, and so you're seeing less of that. So you have certain observations, this is good. That's what humans are. We were curious. Okay. Unfortunately, we don't have something that could tell us how the world works.
Mm.
We have to make our own kind of judgment, what we think, how we think things work. And I think, yeah, the Earth for the longest time would have looked flat for everyone. It still looks flat. But we kind of past that point now because I mean we have satellites already in orbit that can
Absolutely.
take pictures of the Earth. But there's
Yeah.
certain things that you can do. But going back to my point is there's always that aspect of trying to understand the unknown. And so when you then look into, I think for me, I started with like physics,
Okay.
theoretical physics, and now
Yeah,
that's
because
an entirely different.
I was going to ask that when you're in high school, because I kind of suspect that that's where you would start. When you're in high school, what kind of subjects? Is it STEM subjects? What
Subject,
kind of
yeah.
subjects do you start laying grounds? And what kind of activity in high school starts to trigger that desire?
Like this is a great question, by the way. And I think for me it's a very important question. Because right at the moment, like we live in a very different world from our parents. Like the
Yes.
technology has evolved so much that we depend on it. But now it's getting to a point that fewer people actually know how these things work and how they are configured.
Mm.
Everybody uses like a cell phone. Like
Yeah.
I'm not saying I understand the inner workings of a cell phone, but very few people understand that. And there is I'm thinking that there's gonna be probably somewhere where we need to revise, the STEM subjects, if I can
Mm.
put them like that.
Yeah.
Revise the curriculum a little bit. But that's like a next generation thing. But certainly. I had maths, I did
Mm.
physical science as well. And I fell in love with those two from high school. But I also did I did accounting as well in
Okay.
high school. But I
Yeah.
also I also did biology as well. And I think biology is the one that can get people interested very quickly because it's right in front of you. You perform the experiments, you see all these things. Like I was intrigued when we uncovered, for example, the DNA,
Yeah. Wow.
how
Yes.
cells reproduce. Like that was pretty wonderful. And we could
Mm.
see, fortunately, like I lived near the university. So I studied at Rhodes University and they had a
Okay.
biochemistry lab. And so
Oh,
they could
nice.
literally like we had internship there and
Yes. From high
there.
school coming
Um,
in.
from
Oh,
yeah,
that's
coming
fantastic.
in.
Yeah.
Yes. Exactly.
That's fantastic
And
because
so
it
we
kind of
come
gets you
in.
going already. Yeah.
Exactly.
Yes.
That's my point exactly. So you come in and then you actually see the DNA separating from the cells. You can actually now even there's what we call like the DNA mapping of some sort. Like
Yes.
this was even in high school, but
Mm.
you know how you actually extract the DNA to make like a mapping of the DNA strand or something like
Yeah.
that. And this was in high school. I got to learn about that in grade 12 eventually, but biology in itself is a very nice science to get people in because it
Mm.
tells you how even your body works, how plants work,
Mm.
and how we got here in the first place. And it's
In the
pretty
first
much
place. Yeah.
on the desk, all right? Physics and maths is a little bit abstract, and I get it. It's a little bit abstract.
Oh, no.
I do get it, right? It's a little bit abstract at
Mm.
times, okay? Because you gotta be able to think, you gotta be able to put yourself in some situations. You
To
get to see,
understand
like
it.
Einstein has this famous quote where he was imagining, yeah,
Yeah.
it was he's like riding a photon, which is a photon is like a particle of light, and he's
Mm.
trying to picture how would that look like. You need to have that imaginative, like obviously he can't write a photon, but you need to have that imaginative, and then he's kind of thinking mathematically at the same time, seeing the equation, how things would look like. And that's the kind of mindset
I
that you
see.
kind of need in order to, for example, to do
Start
well
getting interest.
physics is quite abstract.
Yeah.
Yeah,
So
yeah,
just
it's
when you
quite
mentioned
abstract.
so, yeah. So when you mentioned something around the fact that you grew up just nearer to a university, it takes my mind to when university organizes open days, and I'm wondering, couldn't this
Open
be
days.
something that is always like on a more regular basis, wherein high schools are given access to various universities to on a more regular basis so they can kind of stimulate students' interest. I don't
Yeah.
know if that is already happening, but I think just from the way you say it, it kind of suggests that if that was, or if that could be, it would be great because when we are young, we really get interested, intrigued by so many things, just fascinated by how the labs are set up and by how equipment in specific places, they can really push us even to go back to school and do
Yeah.
really well. So maybe that is something that
Mm.
you want to just comment on a little bit more about how that really
Comment.
helped shaped your the trajectory.
Yeah, it's certainly seeing things work in the next, like I will say it up front. Having a university near your high school is a great privilege.
Yes.
Um, and Rose University had done an excellent job, like in trying to integrate with the local high schools
Mm,
and bringing students in. Like for instance, I was never in the physics department, but I was brought in through internships in the biology department. But it's still science. They basically use the same principle. But that exposure, it kind of made whatever I was learning in high school now sort of an attachment. This is real stuff. It's not I'm imagining stuff and I need to, cram some few facts there and then just pass the exam, but it becomes more of a personal interaction. It's kind of like when someone learns how to fix a car. If you do it on the board theoretically and you tell them, okay, this is what you need to do, this is how this part works, and
it's
so on.
completely
But when you
different.
actually show them, yeah, it's really different. It kind of links personally to their life that, okay, yeah, I kind of need to know how that works.
Works.
And they kind of now understand. So there is a big part of that universities, and high schools. In high schools, yes, in high school, I must emphasize this.
Okay.
I know teachers are heavily loaded with work.
Of course, they are,
My
and they
teachers
actually
also
love
were
their work.
heavily
Yeah.
loaded with work.
So,
Yeah, they
so
love their work and they're heavily
yeah.
loaded.
So
But there
now
is
let's
an
just
aspect, yeah,
yeah. Go ahead. Go ahead.
there is
Sorry.
an aspect for them there is an aspect for them to kind of do the experiments with the students. Show them that what they're learning in class is there in the real world. Naturally, children are inquisitive.
Yes.
But as soon as something is so abstract to them that they can't even understand where to use this information from, then that defeats the purpose. And a lot of people are discouraged by that. But as soon as you kind of show them, hey, you see the stuff that you learned there? Look at it in play right now. Now you can actually explain what is happening here. And that's what I was trying to teach you all this time. But yeah,
What is your work? You
yeah.
just go to work. You look into a telescope. What is your day like? What is the life in the day of Dr. Charles?
What is a day like at the life of a
What's it? I can
cosmologist, like
imagine. I can imagine how
astronomer?
fascinating it would be just looking into a telescope
Yeah,
and
a
writing down
telescope.
some equations and discussing it with colleagues and students and all their
Yeah,
community, writing about it. I mean,
yeah.
what is it like?
Okay.
I can imagine your job to be such
You know,
fun, like fascinating stuff.
it, it is like it's always a privilege for me. It always is a privilege because not every human being gets the opportunity to know something that no one else has known yet, and I'm part of that group of people.
Wow.
And for instance, for me, when I go to the office,
Mm,
I don't actually take any data from me. I just the laboratory or the observatory gets the data. There's a lot of stuff that goes in there. Okay, there's a
I
lot of
see.
people working in engineering, making sure that the telescopes work. I kind of know what goes on in there because as a scientist, unfortunately, unlike an engineer, you can't ignore everything. You kind of need
Mm.
to know how the data was collected and all
Yes.
that kind of stuff.
Yes.
So you know a little bit about engineering and all that kind of stuff. And you sit in the office, you process the data. We make these very beautiful images of the night sky, but they're very different.
Okay.
The images that we make are very different. These are images that this is how the sky would appear, for an
Mm.
example, if you were sensitive to radio waves. So it's not how the sky actually appears optically, like with
I
your
see what you
eyes.
mean.
When you look at the
Yeah.
night sky, you would see something different. But when you look to radio waves, it's an entirely different night sky. You
Mapping of.
get to
Yeah.
see
Yes.
more interesting things. And that's what we do. We process that data. Every now and then we discover something new.
Wow.
There are these, for instance, right now, we even with our local universe, right, with our local galaxy, the stuff that's like within our galaxy. So
Yes.
so how it goes is in size, we have our Earth, we have the Earth, which is one of the planets, okay,
Mm.
orbiting the sun. And the sun with our nine planets or eight
Mm.
form what we call it a solar system. And that's us right there.
Yes.
Okay. But then you have, if you look at the night sky, you'll see also different kind of dots in the night sky that are there. Those are other suns, if I can put it like that, but we call them stars, okay?
Mm.
And they're all at different periods of their lives and so on. And so
Yep.
you have a solar system with planets around, and then you have another solar system, another
Mm.
star, what you would see in the night sky. You won't see the other planets orbiting around it, but if you have a powerful sensitive telescope, you can see it. Okay.
Mm. Are you
You
able
can
to
see
share
that
some
there
of
are
these
planets
images with
orbiting around.
are you able to share some of these images with us so that we are able to, kind of let the audience see what you're actually describing? That would be absolutely fantastic.
Uh,
So
yeah,
if that is permitted, if not, I think I'm sure they'll find a way to see.
that's
Take us deep into the galaxy. Take us deep
into the galaxy.
into what you see and how that affects us, people on one
Yes,
of the planet. Take us deep into the galaxy, the solar system, all of that,
all
and
of
then
that.
tell us how
It
is
affects
directly
us.
impacting or affecting us as humans or as a
Yes,
species on this planet.
yes, yes, yes. Um, okay. Well, let's maybe conclude from here.
Yes,
Solar
please.
system.
Yeah.
Several solar systems, you form what we call a galaxy.
Okay.
So we are in our Milky Way galaxy, and there are other galaxies out there. But I'm going to
Mm,
focus just within our galaxy. Okay.
mm.
There's a lot of stuff that happens in our galaxy. For instance, our sun, right, is not how should I say this? It's not very friendly at times. There are outbursts
Okay.
that it does on some
Yes. The pulses. Is
outbursts
that
of
what you refer to
radiation.
as the pulses?
No. These are flares from the sun.
Okay.
So the pulses are a little bit different. So
Okay.
these are flares from the sun when the sun decides to eject some ionized particles. And
Mm,
those particles, sometimes they can affect things on Earth.
I
Sometimes
see.
they can affect power lines. Sometimes they can affect satellites in orbit. They could fry
I see.
equipment there. So the sun isn't so friendly and nice. It does things because it's a huge hydrogen bomb inside there. It's
I
basically
see.
nuclear fusion going on. It's really hot, so it's very energetic. So sometimes it explodes and then it does all these things. How does this then link to us?
Mm,
Interestingly, like I said to you, there are other stars out there, quite different from our sun.
okay.
Okay? These stars can sometimes undergo, when they grow, eventually our sun will do that as well. They grow, they start burning what we call hydrogen inside them to nuclear fusion, but eventually they run out of fuel of burning. And what happens is that the entire sun just collapses and it undergoes a supernova event. So it basically explodes. We see this all out in the night sky. Now, how does this affect human beings? Well, it turns out all the gold that we have, all the heavy, okay, actually all the gold, because gold does not naturally form. It forms inside these explosions. What that means is probably somewhere when the Earth was forming, okay, there were nearby supernovae events that were happening nearby to us. And
nearby
these
to the
might
Earth.
have nearby to the Earth, and these might have triggered mass extinctions as well, because those explosions are pretty much violent. I remember asking, a colleague of mine, like, actually, why don't we have these supernova, interesting stars close to us? And he kind of pointed me, reminded me that, well, if they were close to us, we wouldn't be here because
Absolutely. We'll be fried up or
we'll be
yeah.
fried. Okay.
Yeah. We'll be like other
And
planets
so
that are very hot. Yeah.
yeah. So it kind of changes your perspective that there is an element that human beings, you need to fight against nature to survive. Naturally, things are not so friendly. The dinosaurs, I mean, evolution is pretty much set. That's a fantastic science, how life evolved from a single cell organism like that. But the dinosaurs were around, and then an asteroid came and wiped them off, and then we came into play. Asteroids are still in space. They're out there. NASA is doing a great job of mapping them, but these are direct impacts. They are threats to our survival. An asteroid hits, sure, there's going to be a population drop significantly because a lot of the atmosphere of the Earth kind of changes a bit. So once you kind of understand how the universe works, it begins to inform policies, for an example.
Yes, because
Right?
that's where I was starting to go to say this
Yeah.
must affect your work must have impact on specific kinds of policy, especially about how they work towards preservation of our planet is. You could call it warming, you could call it cooling, whatever the terminology is. But it means that it looks like your work directly has impact on science policy for various governments across the world.
Indeed, that is the case. I think the more we better understand how vulnerable the Earth is and how precious it is, because we've adapted to this only one planet. But as soon as you kind of understand that framework, there are certain things then you begin to try and push for politicians, for example, to implement. For example, there's climate change. You try to reduce the amount of carbon that you put
The atmosphere.
into the atmosphere, yeah, because you don't want a greenhouse. You're trying to run away from a complete climate change because we adapted to this climate. Okay, you don't want to have that. Other things, for an example, we have satellites all over space, and there's people are building cities everywhere. But the biggest problem with that one is now there are fewer places to put telescopes. And once there are fewer places on Earth to put telescopes, then we have a much bigger problem because we can't even study the universe itself. We can't know, we kind of limit
Our
it
own
because
safety, if you like.
for our own safety, we kind of pollute it now. And so you try and you push for that. You try and inform policies, like you speak to politicians. It's a big job that we do as
Yeah, so
scientists.
briefly, because you've just said something that's really, really, really strong. You're saying that if we pollute our Earth, we're not going to have a means of seeing what else is around us and how that endangers our lives. That's a very
Our life.
strong point.
Yeah,
That's a very,
yeah. It's one of those things where we need to preserve the earth for the future generation, for
yeah.
them to have the privilege to even study, get to know about these things. If the entire night sky is polluted, climate change has already taken over, the atmosphere is thicker, we have a lot of things that change. Our instruments can adapt, but only to a certain extent, right? Um, right now, for instance, we cooperate with Starlink because Starlink has satellites all over,
Okay.
and sometimes when we're doing observations, sometimes they do switch off their satellites so that they don't interfere with our observations of the night sky.
Mm.
Trust me, like this is the one thing which uh, it's very bad in a way because there are some times where you're trying to work out something scientifically, trying to create these nice images. I mean, after you've worked out those images and all that, you get to learn about the dynamics of the night sky. But if there's a satellite passing by, it interferes with everything, and now
I
you don't
see.
get to learn the true nature of what the night sky looks like. Okay, you can't even test your theories and all that kind of stuff. But yeah, so we kind of need to preserve our night sky, our planet for future generations so that they could learn. And there's no doubt that we're here, unfortunately, and we have to survive.
I just want us to talk about a little bit on if we don't have a place to put telescopes. I really want you
Yeah,
to talk on that a little bit more. If we don't have a place to put
yeah.
telescopes so that we can see our our
Telescopes.
environment
Yeah.
around our planet and how that impacts our livelihoods as a species and how it impacts the planet. So
Yes.
thank you, Dr. Charles. I think that some of the ideas that you've shared with us is absolutely encouraging in terms of, I was just thinking that astronomers just go and look into the telescope and enjoy this magnificence of the cosmos and magnificence of the beauty and all sorts of interesting things happening in a galaxy or solar system or whatever. I don't know what they really are. I have very basic knowledge of the solar system, etc. So just share some information about how your work and people in your community affects policy.
Okay. Yeah, so certainly, like, I mean, one of the things that we do is, again, mainly research. And, we sit and look at nice, beautiful images, and extrapolate some astrophysics there. But there is an aspect of our work where is to, drive policies
Mm,
within our framework.
yeah,
One of which is the we kind of have a driving influence into trying to preserve certain regions, certain demarcations, for an example, to
mm,
try and preserve them for radio telescopes. Now, I'm making an example now of, for example, of MeerKAT. That entire
mm,
region there is a radio quiet zone. Like no one is allowed to use any mobile cell phones within a 100-kilometer radius from
mm.
the actual array. Okay. Um, and that's great. It does impact people's lives a little bit, but also what it does is it brings how should I put this? It injects money into the
Mm.
local economy.
Okay,
Now, so we drive the science. We want to study what the universe is like. Other people benefit from that because the locals get to build those telescopes. People gain technical skills. So, in as much as we're trying to push for the science, we're also driving policies regarding employment, community outreach in that specific region that we're doing things. So, there is research, but there's also a societal impact that we always had on the side as well,
I
which
see.
is yeah, to bring more economic empowerment in the local community,
Mm,
upskill people. For an example, research as well, what
mm.
it also does is it drives innovation
Correct.
because whenever you have a problem, you try to fix it, which means you need better technology. And governments pump money into that as soon as they can see, oh, let's do this. And then as soon as you have a collective of people doing that same thing,
Mm,
then it drives technology. Once it drives technology, inevitably our lives improve. Make an example. When J.J. Thomson was discovering the electron, no one knew that it will eventually be used for the electron microscope, for an example. No one
I
had
see.
the idea at the time, but it eventually led to a marvelous technology. But initially, he was just trying to discover what makes up matter. It's the exact same thing. For Africa, for example, I'm going to speak mostly about Africa.
Yes.
I feel like when it comes to optical telescopes, when it comes
Yes.
to radio telescopes, okay,
Mm.
we have sort of an advantage because South Africa, like Africa in general, is mostly radio quiet. It's mostly there's certain regions, Africa is big, and there's certain regions that are just not populated by anyone.
Yeah, what is
And
radio
so
quiet? That's a very interesting. What is
radio,
radio quiet? Yeah,
yeah. Radio quiet basically means that within a certain radius, there are no radio emissions.
I
Like
see.
it's unpopulated, so there's no radio signals. There's no cell phone signal, for example. So
Correct.
you don't have radio within that region. You can't get anything. Like it's basically just quiet. And those are good grounds where you want to
Mm.
have telescopes. And that's where we feel that in order for Africa to catch up with the rest of the world, and this is our prime, we built the telescopes here. We invest, governments, we lobby governments
Mm.
to invest, bring the telescopes here. But once they're here, then the governments need to invest in the youth.
Correct.
Invest in the youth, get them not to just study the engineering aspect, maintaining the telescopes and so on, like the basic skills. There is a side to it where you want to develop the necessary catch up in the science with the Western world so
Mm.
that they could effectively use that instrument, okay, and figure out their own things that they could put in paywalls because information is proprietary. Like we
Correct.
can't escape from that. But once those telescopes are built in,
Mm.
every government gets a share of that telescopes, and it's up to the group of people within that community that get to use that, advance that data, and make their own science conclusions and make their own science discoveries, which then enhances the next generation of people. So there are two aspects. There's engineering, great.
Yep.
You upskill the local community,
Mm.
upskill people in general, but there's also another advancement where you try to catch up with the rest of the world, where now you actually have to invest in scientists. So we actually have those policies as well, where
Mm.
we try to lobby governments to invest in students doing research, science topics, okay? And funding students. I mean, the biggest thing is funding
Mm.
in most students and like everywhere in general. As
Mm.
soon as there's funding, students will pour in. When you do that investment, there's a higher return within a 10-year gap. That's what the Europe, US, that's what they do.
Mm.
They bring in the people, they fund them. They know that the investment on the return on that investment is extremely high.
I see.
And that's what, so in as much as we try to do science, there is a social impact that
Correct.
we try to navigate, push towards the country. I'm speaking like for Africa and South Africa in general,
Mm.
but that's
Mm.
what we inform those kind of policies that look, this is a great opportunity. Let let's invest in this.
Take, for example, when the AU is sitting, do people like in your community, astronomers, go to the AU or go to accompany heads of states to various kinds of meetings to make presentations? Do you participate in intergovernmental kind of spaces wherein you are able to make articulations about how the research is going and so on, or is it just something that is only for the academic community?
Yeah, certainly we have societies as the Astronomical Society. We have the African
Okay.
Astronomical Society. It's like it's a big society that
Mm.
that manages all the astronomers. So they're the key policy makers. They
Correct.
drive the policies. So they're the gap between the researchers and the politicians, if we can put it that way,
Mm.
the people who are in charge of different countries in Africa.
Yeah.
And so we communicate, like most of us are members in that society. And
Mm,
so annually, there's ever a conference, and then we look at, okay, how are we going, what's the policy framework? How is Africa looking in general? What's our next goal?
mm.
Where are we going? And we try to make a collaborative effort. So there is a little bit of, okay, there's this kind of science that we want to do. Society, how could this impact this?
Mm.
And then we try to formulate policies that we can then communicate to,
Yeah.
the AU, for an example, the African
Mm.
Union.
Yes.
We communicate, and then they invest money. To tell you this, the AU actually funds a lot of the money, actually.
Oh, fantastic.
They do
Yeah.
fund students, and that's because they see the value in this. All right.
Mm.
We show them that output. Look how many students you've invested in. The more you invest in the youth, the greater um, the return in that country. You uplift everyone
It's a
in that
powerful one.
sense.
Yeah.
Yeah, you kind of uplift everyone, which kind of makes the country in itself
Has
um,
continuity.
yeah, continuation, continuous improvement. And so that's what we do. There are unions. And then internationally, there's the Astronomical International, the IAU, which is the International Astronomy. Okay, I can't remember that. It's the IAU union, and that's a bigger body. So there's
Oh,
the
yes.
African side, and then there's the international.
Yes.
So there there's a big shift in, okay, how should we, for example, protect the night skies? Because now we have conflicts with, satellite companies, people bidding around observatories. So we're trying to preserve certain things about, the night sky where we want to build telescopes. So that's a much bigger framework. So they deal with governments all around the world to try and formulate policies that can, number one, protect, for example, astronomy, the
Mm.
discoveries made in astronomy, protect,
Yep.
okay, we need to preserve certain regions. Also, how can we invest in the youth to keep astronomy going?
Mm.
The more you pump in money in this, the better, the more technology is actually driven eventually, like the example that I made
Mm.
about simple things like just doing basic research, that drives technology a lot. The more people work on a certain subject, then there are more ideas. And the more ideas, that drives technology, different ways of doing the exact same thing. And so there is that bigger umbrella, which is the International Astronomical Society Union. I think it's
Yeah.
society or union between the two, but they deal with intergovernmental policies. They inform those policies to try and protect radio astronomy, and it's a wonderful thing. So, in as much as you go to work and you look at images, but that's not the end of it.
I
There's a
see.
larger responsibility. You got to think about these things as well.
So I
But
also
yeah,
understand that you go to MeerKAT.
yes,
What I did get on the news quite a while back was that this was a square kilometer array, very fancy sort of space. But for the ordinary person, what is a square kilometer? What activities are going on there? Besides that, news cameras go there and we see quite a lot of telescopes pointing towards the sky. Can you just share with us
yeah.
inside those telescopes, what's happening at the MeerKAT?
What's happening at the MeerKAT? MeerKAT is a fantastic instrument. What we're trying to create there is a telescope that is uh 8 kilometers. Right now, it's like 8 kilometers in stretch. Like
In
it's
size?
it in size. Like,
Wow.
and it's physically impossible to build a telescope that big. And so what you do is, rather than building an entire telescope, like an antenna that big, because structurally that will be very fragile. What you do
Okay.
is you build smaller ones. That's why it's an array, not like
I
an
got
entire
you.
telescope by itself. So you
Yes.
build smaller ones, and what you do is there's some clever way of combining signals from all those
Wow.
different antennas,
Okay.
and they all act as just one gigantic antenna looking
Now
into
that's
space.
interesting. That's
Yeah.
fascinating stuff. So in the array, you have all these antennas that
Yeah.
somehow work together as a single unit. And
Unit.
now
Yes.
then you get to see the cosmos just by this 8 kilometer thing. That's what you are saying.
Yep. So it's as large as that. And now, I mean, that's the current status of the array, but they're going to build those spiral, we call them spiral arms that, spread out from the center. Okay.
Mm,
And the larger you can make those, some of which they're going to probably incorporate other African countries. And so it's going to become even larger. And the
okay,
more larger you build that telescope, the more clarity you get from the night
with
sky, the more resolution. When I speak
correct.
resolution, clarity in that image that you get, there's more detail that you can get. The more
Mm,
detail that you can get, the better the science that you can do with that telescope. But it also means the greater the engineering challenge. So it's both like an
mm,
engineering challenge. It's like it's a challenge in all frontiers.
I see what you mean.
Discoveries, it's a challenge because there's more that you're gonna learn. Engineering, it's a challenge because there's more that you gotta deal with. You gotta figure out how you're gonna make optical cables this length. High data volume because the more antennas you build,
Mm,
the more data volumes come in. And then you
yes,
gotta build supercomputers. You gotta find ways to compress that data, clever ways to compress that data, but not lose information at the same time.
yes.
So so it's a really wonderful instrument, and it's the world's best. It's the most sensitive
Well,
instrument in the entire world. Like it's the most sensitive radio telescope in the entire world.
so in the entire world, we in South Africa, we have the Square Kilometre Array that is the most sensitive equipment of its kind. That is an incredible
Yeah,
infrastructure. That
yeah,
is an
yeah.
incredible piece of infrastructure. And I think that,
Hmm.
like you were saying earlier, which means if you have spaces, pieces of real estate in other countries, you can build similar infrastructure, which you can still link. That's going to be
Link,
very
yes,
massive. That's going to really draw quite a lot of attention to your area of study and the work
mm,
that you do that can impact globally. So you have people coming from
globally.
other countries and from other countries into MeerKAT?
Yes, indeed. Like we collaborate with other people from other countries, and and science is kind of forcing us now to work together as countries. Unfortunately, that
Okay.
that is the deal. We have to work
Yeah.
together, and our
Mm,
politicians have to sit down, find a framework how we can, have a working relationship. That's how it is. For an example, um, there's an image of a black hole that
okay.
had circulated in sometime in 2017. Let me just briefly explain what a black hole is.
Go ahead.
So, you have our star, like the sun that we have right now, and
Mm,
that's made of gas. So, gas, what happens is that gas eventually clumps together because gravity is pulling things together. So, what gravity does, it pulls every mass towards each other. So, it's like a magnet. They attract each other. So, the gas particles, they
mm,
attract. But then when things are getting attracted, okay, they begin to compress and they heat up. And that's what basically happening with our sun. Hydrogen is being compressed into small spaces and it's heating up and then it's doing some nuclear fusion. Now you can imagine the case that the star was so big, was this
mm,
big, right? Much bigger than our sun. It had so much gas in it, okay? When it formed.
mm,
And now, when it runs out of that burning fuel, okay, because there's this inward pressure of gravity trying to pull things in, but
mm,
that nuclear fusion kind of pushes things back out. So then
mm.
the sun becomes stable a little bit. But eventually, the fuel inside runs out.
Correct.
And when it runs out, the entire thing just collapses and undergoes a supernova. Now, depending on the initial mass of that star, it can form a black hole. And a black hole is just one gigantic dip in space that light itself can never escape. So that's why we call it a black hole because light cannot escape from it, it looks dark.
So
Um,
how do you see into
like
it? Do
you
you?
you just see the stuff around it.
Oh, I see.
That makes sense.
Yes, it
Yeah.
does. Yeah.
Yeah. So
So you
you don't
see
see
things
the
around it, but
black
you don't
hole
see it.
around.
So,
You don't
okay.
see it because there's no light
There's no
coming from
light
it.
escaping.
Yeah.
Makes
So
sense.
how you know it's there is by looking at the surrounding.
And that surrounding then
Okay.
provides useful information
Useful in
that
yes,
impacts
yes,
your ecosystem,
your ecosystem.
the ecosystem.
Mm.
Okay.
So now
Interesting.
if you want to learn about these black holes,
Mm.
the black hole that they had to image, it needed a telescope the size of Earth. Now, how are you going to build a telescope as big as the size as big as Earth? There's no way you're going to do
Yeah.
that. The science kind of says if you want to have details of this black hole, you kind of need to
Mm.
build a telescope this size. And countries had to collaborate. We basically had antennas all around the world, all looking at this black hole, and we combined the signals together in some clever way
And
with
analyzed it.
hard drives. We had to
Mm.
bring the data in, and then it was an entirely beautiful collaboration of international telescope all laid around the world. And then they made that beautiful image. And that's MeerKAT is now being incorporated into that very same network. We call it the VLBI network. So very large baseline parametry. We're now very large baseline means bigger, better resolution than
Mm.
any telescope. It's a telescope the size of Earth. And that needs governmental cooperation. We got to work
Cooperation.
together. Yeah.
Absolutely. So it's kind
So
of, so
yeah. So
your work is bringing politicians that normally wouldn't sit together, friends and foe are collaborating for humanity, as it were. Okay,
yeah.
so just
Yeah.
talk to students that are going to watch your podcast and they're going to be so interested in astronomy. Talk to them. What should they really be paying attention to? High school.
High school. Yes, so certainly the STEM subjects are still, I mean, they're very difficult, I must say. Not
Mm.
very difficult. They're not very difficult, but you got to put a lot of effort in. And the key thing is to put a lot of effort at the early stages.
Okay.
Because once you've already grasped the material at the early stage, it's easier to now understand the other layers once you've got the foundation properly. A
Mm.
lot of people tend to miss that part. That's why in high school, it's crucial that if you don't understand something, ask your teacher. Have someone, but especially right now, you have access to YouTube. I always told this to students. You have access to YouTube. Back in the days, we didn't probably, when I was a student, certainly. Um, Wi-Fi was not around at that time and all that
Mm.
kind of stuff. But there wasn't much you could do if the textbook is not clear enough or your teacher is not clear enough. That's it. But now there are people on YouTube that make videos to try and explain science concept. So you get up, you work. That's the first thing. The minute you start doing that, it becomes a habit. You train yourself from high school, it becomes a habit. You do your mathematics, your physical sciences, um, biology as well. It's a really great
Yeah,
combination.
your favorite,
You're
your
my
starting
favorite, yeah,
point. Yeah,
as
yeah,
well. In my starting point, it kind of
yeah.
teaches you the basics of science, like in a nice, confined environment. And
Mm.
and that's what you need. That's what you need to really do. But you strive for understanding rather than getting a distinction or full marks. Strive for understanding, because eventually, when you get to university, now you're going to need that entire understanding. Sure, undergraduate, you could probably do around with not understanding everything fully. But once you get to research, no one is giving you marks there. This becomes personal now. It's you actually inquiring. There's no, oh, there's a distinction or something you did.
Mm.
No, it's about you now being inquisitive about your work. And
Mm.
so there's a lot of attachment in that. And if you build that at an early stage, that's what I advise you to do. If you build that in an early stage, it becomes a habit. And science becomes like a personal relationship that you have with the universe
Mm.
itself, because you get to sit in this privileged position where you understand something that not a lot of people understand, which is
I like
basically
that.
how the universe works.
Absolutely, I like that. And then
Yeah.
the business, the entrepreneur. How does astronomy influences entrepreneurship? Where can we start a business from astronomy, from the work that astronomers do?
Fantastic. So let me start off here. Besides okay, maybe it's not quite obvious, but there is the aspect of building the telescopes.
All right.
And there's a lot of components that go in there. And in South Africa, for example, we have a company that makes receivers. It's a South African-owned company. They make the best receivers in the world right now. They're the best at like making receivers, and that's because they had the drive to do that because they had to build MeerKAT, and so they had to constantly trying and improve, and they became the best. Now they build receivers for military companies, not just now MeerKAT, but they've branched out because of that. There's more also on managing the data centers. For an example, with MeerKAT, now you have private companies who then come in, they install the fiber optics, they manage your servers, um, and they do business with the government basically on a daily basis. There are companies that build something that we call the correlator that sits basically as an electronic component that sits there. Companies, there are companies that are just dedicated to just building that component by itself. Now, the other thing is the telescopes eventually are going to have to improve.
Okay.
Which means now we need more people to actively do research. If you look at these European companies, they work with universities to put the research into practice.
All right.
So the research output from the universities, they work with the university research groups, but they're more in the industry. And what they do is the output that they get from the engineers that actually do the research at university, they built the stuff. They built and test, and then they slap what's this thing called? Uh, when you're trying to own something, is it
A pattern or
yeah, pattern. Yeah, they
yes.
pattern it, okay?
Yeah.
And that brings money to them because now they're able to do that in cooperation with the universities. And that's something that has always been the case in Europe. But I was very proud to have South Africa actually doing that kind of thing, that we are patenting a lot of stuff that is manufactured locally. So there's that as well. And then there's the managing of the instrument itself. So upkeep, regular maintenance. That brings in different group of guys that do those things as well, businesses that do those things as well. But there's another aspect where it's now outreach.
Okay.
Different organizations have that aspect as well, where their core mandate is to actually just spread the information, they communicate the science. So there's a lot more that you can do, like for entrepreneurs, that they can do to benefit from just having MeerKAT or radio telescopes within South Africa because you have access to it. Like James Webb Telescope, for an example, is American owned and European, and but that we don't have part in that. So you're kind of limited, okay, in how much you can do with that. But because MeerKAT is in South Africa, for an example, you could have a YouTube channel where you just, you go and walk around, shoot every events, everything happening. You catch on to what happens in MeerKAT kind of data science. Perhaps you might get a following from that.
That's a fantastic one. Yeah.
Yeah. There is that it's kind of a soft thing, but because you have access to the world's best instrument and scientists locally, there's that play field now where now you're trying to bring that up. And then you bring exposure to the instrument, but at the same time you're benefiting because you you know you're getting more people to watch your network or something like that.
Where is your research? Where is the big thing that you are looking into now? That is one of the questions I also meant to ask. What is the next frontier? What is the thing that that you are working on as a piece of research now? And how impactful do you think when it's completed that it will be?
That we're working on right now.
Yeah. Yes.
Right now, what we're trying to get to in cosmology, this is the biggest mystery, well, not the biggest mystery. We have an idea of how the stars and the galaxies formed. We have an idea. In other words, what I mean by that, we have simulations. But these are always ideas, so long as the data is not there. And the reason why we have large sensitive instrument is because if you want to probe these kind of errors, you need a lot of sensitivity. Like sensitivity in the sense that you need to measure the same thing over and over again so that you get deep enough into the universe, to uncover that error. Believe me when I say parts of the universe that were left over from the Big Bang are still here. The universe is very old, about 13 billion years old. But its signature, what had happened during the Big Bang, it's still out there. All we need to do is to look out into the night sky. And there's a whole science argument that you can frame how you can do that. And all you need to do is look out into the night sky. And so what we're trying to do is answer this question, nail it down. How does the universe form? How do we get from no galaxies to galaxies and to our current state of the universe? We have computer simulations that can produce our universe, okay? But they need refinement a little bit. And the biggest drive right now is to get that one set of simulation that can actually produce our universe in its precision. That's what we're looking for. That prestigious, highly redshifted 21 centimeter signal coming from the cosmic dawn. We're heading there. Our instruments, our data is telling us that we're heading in the right direction, but there's still more work for us to do. That is worthy of a Nobel Prize. It's a bigger collaboration, so it's not just me. It's like an entire people that work in that field. So it's not just me, myself alone, but it's a collaboration of people, and that's what we're trying to basically do. And once we got that figured out, then it's another filled in gap in our understanding of the universe. And that's what I'm currently working on.
Fantastic. Ash, the podcast will be coming back to you when we get this big breakthrough, I should say.
Yeah.
Thank you, Dr. Charles.